Okay, good morning to everybody. It is for me a real pleasure to introduce you Professor Michl. It is quite unusual that the presentation of this series of lectures is not given by Augusto Sagnotti and Chiara Cappelli, who are in charge of the Colloqui of the Classe or della Classe di Scienze, which are the most prestigious colloquia that the Scuola Normale organizes during the year and are intended as general speech by leading scientists in the world in the different topics and conceived for being of interest for the general audience of the Classe di Scienze della Scuola Normale, which includes mathematics, physics, biology, and chemistry. But I am very happy of this particular absence of Chiara and Augusto, because that gives me the opportunity of introduce Professor Michl, who will speak about on the following Professor Ciamician, who is one of the leading Italian scientists toward solar cells, which will be the topic of the conference. The only problem I have to introduce Professor Michl is that his CV is so large that it is impossible for me to follow all his honors and achievements. I just remember that he's Czech of origin, but he is, I don't know if it is Czechia or Slovakia, because Czechia, sorry, because this would be a problem, but he is in the United States by 70s, and he has occupied a number of prestigious positions as a professor in different places, including in particular Boulder, Colorado. And he has received a number of prizes. It is impossible for me I can just show you a short CV of Professor Michl, which doesn't include any discussion. It is just a long list of positions, prizes, achievements, and so on and so forth. By the way, he is also fluent in Italian, which is an aside which is not very interesting in this context, but it is very pleasing to speak with him also in Italian because he likes to speak in Italian. But apart from that, I'm very happy to follow his discussion about the perspective the contemporary research has in the direction of sustainable energy, and in particular solar cells, because apart from the specific scientific items he will for sure show to all of us, it is the general perspective of a leading scientist in this field, which could be very important especially for a younger researcher to put this research line, which is on one of the milestones of the contemporary research, in the proper perspective. I am sorry for not having given an exhaustive list of the different achievements, etc., of Professor Michl, but I prefer, knowing him, to present and to give you the opportunity of follow his general view about science and about this topic. And thank you for being here, and I let you present us your lecture.
Thank you very much for the invitation. It's a privilege and a pleasure to be asked to speak here. I'm glad that I've been left a little time for the talk. The vita is really not so interesting. I hope the talk will be somewhat more interesting. I come to Pisa actually twice this year, and when people ask me why, I tell them I need to help support the tower, the Leaning Tower. The subject of today's talk has to do with climate change, basically. We have a very varied audience here, and so I will not go into any details in anything that I'll say. If you want to ask me questions at the end, please go ahead and do. So let me start with a dedication of this talk to Giacomo Ciamician. I started my independent career as an organic photochemist, and Ciamician is the father of organic photochemistry. He started it in Bologna using sunlight as his light source, which was easier to do than it would be in, say, Denmark or Norway. And he had a vision that he actually published more than 100 years ago of getting rid of smoking chimneys, of smokestacks, and instead powering industry with solar energy. And he would be amazed that today we are about to actually accomplish his dream. The work that I'll talk about is done partly in Colorado, at the University of Colorado in Boulder, and partly at the Academy of Sciences in the Czech Republic in Prague. I have research groups in both places, and I support the contamination of the atmosphere with CO2 by flying 10 times back and forth over the Atlantic. The work is supported on both sides of the Atlantic, and as listed here, and it is done by several people whom I'll mention during the talk. So, climate change, what is it about, and what is threatening mankind right now? It's stated here on the second line. More carbon dioxide in the air will cause, or is already causing, the warming of the Earth's surface. And this diagram here shows the future of the temperatures on the surface of the Earth as a function of what we do as mankind. Depending on how much by how many percent we reduce the emissions of carbon dioxide, one or another of these curves will be followed, and time is plotted on the horizontal scale. It's the time when we start the reduction of, maybe I shouldn't be standing here, it's causing trouble. Well, that's even worse. Okay. So as you can see, if we do nothing at all, no reduction, just continue to emit CO2 at the rate that we are now, it will not take very long before the peak temperatures will be higher by 10 degrees. If we start reducing, say right now, by 2%, it looks a little better, but ultimately we'll get the same problem. If we start reducing the emission of carbon dioxide more, say by 6%, well, we'll postpone the inevitable. From this graph, it's clear that it's not enough to reduce the production of carbon dioxide by a few percent. We actually have to decrease it dramatically in order to avoid very large increases in the temperature. And if one asks then the question, why is it that adding CO2 into the atmosphere causes the warming, then the usual explanation that's given to children in schools is the greenhouse effect. People say, well, the atmosphere transmits the UV visible radiation from the sun. That reaches the surface, warms it up, and then the surface emits, and the atmosphere absorbs much of the IR radiation that's emitted by the surface. Most of that absorption is done by water. If we actually didn't have water in the atmosphere, the average temperatures here would be something like 20 or 30 degrees lower than they are now. For me today in Pisa, that would not be so bad. But overall, we would be in a permanent ice age. So the greenhouse effect, mostly due to water, is actually beneficial. We are adjusted to it. Life on this planet is adjusted to it. But the argument is that by adding CO2, which provides additional absorption of infrared radiation, we do not allow the IR radiation to escape into space, and that causes the increase in temperature. Now, this argument is not quite right, because the amount of CO2 in the atmosphere already now, and even if it were lower by a factor of 2, is sufficient to absorb all of that IR radiation in the spectral region where CO2 absorbs already anyway. So if we double it, we cannot absorb more than 100% of it. And so it should make no difference. And there are indeed people who argue that all of this science that has to do with climate change and global warming and so on is a hoax because of this argument, or because they stand to make more money if oil or coal are burned, or there are some other reasons. But the real explanation is a little complicated, and so it's not usually given to the general public. But I thought it might be interesting to mention it in this, to this audience here. And there's a specialty name for it. It's called positive radiation forcing, and it works approximately as follows. The sun emits radiation that corresponds roughly to a black body radiation, and that at a temperature of about 6,000 degrees. That's because that is the temperature of the surface of the top of the atmosphere of the sun. The sun is much hotter inside, but what determines that radiation that is emitted is the surface of the atmosphere of the sun. And that's very hot. And that radiation indeed penetrates the atmosphere quite readily and reaches the surface of the Earth where it is absorbed. Some of it is reflected, but much of it is absorbed. And then the Earth's surface is warmed, and the temperature that it has is roughly on the order of 300 degrees Kelvin. And so it also emits radiation, black body radiation, but at much longer wavelengths because it is much cooler. It's only 300 degrees, not 6,000. And so it is mostly in the infrared that it emits. Now, that infrared radiation is absorbed by the water and other constituents in the atmosphere, including CO2, and re-emitted, and it is ultimately in some sort of equilibrium at the top of the atmosphere of the Earth. There's a certain temperature that's established, and what goes into the space out is dictated by that temperature. Now, that's stated here. So at equilibrium, the Earth's surface temperature is affected by the rate of radiation from the top of the atmosphere into space. Now, if we increase the concentration of CO2, then more of the absorption will happen sooner, closer to the surface of the Earth. The surface emits the radiation. If the concentration of CO2 is higher, all the radiation in the infrared that can be absorbed by CO2 will be absorbed anyway, but it will be absorbed sooner, closer, at lower temperature, at lower altitudes. And that means that the higher altitudes will become colder. And because they are colder, the black body radiation from them will be smaller. There will be less energy emitted. And then the equilibrium would be perturbed. And so what will happen is that the surface of the Earth will increase its temperature until an equilibrium is reached again, and the amount of heat that is sent out into space is again what it should be. But in order for it to be that, one has to increase the temperature of the surface. So the surface gets hotter. This is probably too complicated to explain to the general public, but there's a lot of science behind this, a lot of equations and so on. So what are the consequences of the increase of the surface temperature? Most of them are not very pleasant because we are adjusted to a certain temperature and everything is adapted properly for that. A change in that will be unpleasant, it will be survived, it will be very costly, and it will cause major disruptions. Are listed here some of the items in question, right? The unusual weather, the melting of polar ice caps, sea level rise. Not only because all the ice will ultimately melt, but also because the water itself in the oceans will be hotter, so it will expand. And if you think that we have difficulties now with a few million refugees in Europe, imagine what will happen when 30 or 50 times more refugees will have to leave places like Bangladesh. Where will they go? Death of coral reefs, more drought and fires, intensification of storms, possible disruption of Gulf Stream. If that stops, that would be a major disaster for Europe and elsewhere probably. Diseases, animal or human or plant diseases change. Tropical diseases will reach places where previously they did not exist, and so on and so forth. So the consequences are mostly unpleasant, and it would be nice to avoid them. You have all seen pictures of the evidence for the changes that have already occurred. Arctic ice in 1979 and in 2012, same time of year. The glacier on the Kilimanjaro, or snow on the Kilimanjaro disappearing, and so on and so forth. I have here a list, actually two lists, of temperature anomalies in the northern hemisphere. What is shown here is pretty much twice the same thing. The top row of pictures comes from a collection from all weather stations in the northern hemisphere. This bottom line comes from the data obtained by a selected number of them, but they're basically the same, so we can just look at the top row. What it shows there is a few decades. The latest is the first decade of this century, and before that we have the last decade of the previous century, and so on. And what is shown are the temperatures that were reached during the anomalies. So if you have an unusually hot sequence of days or unusually cold sequence of days. And this is all in the summer. And as a background, we take here how it was in the years 51 to 80. And it is shown that if you assume that the average is at 0, and you take 1/3 of all these anomalies to be over there around the 0, then 1/3 was hotter than that by 1 or 2 or maybe even 3 degrees, and 1/3 was colder by 1 or 2 or 3 degrees. And you could say that this was the original standard distribution. And the number 0.1% tells you that there was almost no instance in which the anomaly would exceed 4 degrees. So that's the standard. And now this is how it developed over the decades, such that now the average is higher by a degree or so. This red region, which shows the hot anomalies, is no longer 1/3, it is 2/3. And there is now about 10% that are even hotter than anything that we had over here. And the cold ones are less than 10%. What used to be average is 15%. This is a lot of statistics. This has data over many years from many places, and it's difficult to argue with. So, since most scientists who study climate and physicists and climatologists and others are quite convinced by the data that have been collected. It was possible, actually, and this was a big political success, to reach the Paris Agreement, where governments agreed to do something about the problem. On this map, I show in green all the countries whose national academies supported this activity. But there are many other such maps that can be shown and produced. It is true that there are a few percent, certainly less than 5%, of people who are active in climatology who say that all this is just natural, has nothing to do with what people cause or basically deny the climate change. And that is not surprising, because about the same percentage of people will argue that general relativity is wrong. And the same percentage will argue that quantum mechanics is wrong. And there's a substantial number of people who believe that the Earth is flat. So you'll never have 100% agreement on anything. But the degree of agreement here is truly convincing. What will be done about this? Well, if we are not to add CO2 into the atmosphere, we have to get energy somehow, unless we want to go back into the caves and live with torches. And so you can start asking, what would be the sources of sustainable energy? Where can we get energy that does not cause damage to the environment that we live in? And this provides a summary of the sources of sustainable energy. It does not include things like nuclear fusion. Nuclear fusion holds a great promise that in about 30 or 40 years, perhaps, it will be a good source of energy. It held that same promise in the middle of the last century, but it was also about 30 or 40 years. And so it's difficult to count on it. So with that exception, I have here the major sources of what could be sustainable energy. And they are expressed in terms of how many terawatts they could produce. To give you a scale, as shown here, we are now using about 15 terawatts on the whole Earth for mankind's uses. And just extrapolating from the growth in countries like China and India and others, and even in the industrialized world, it is estimated that something like once more that amount of energy will be needed by the middle of the century, and more than twice that by the end of the century. There is no doubt that mankind will use more energy unless it manages to extinguish itself by a nuclear war or something. And so where will that come from? Well, some of it can come from biomass, and if we used all cultivable land which is not used for growing food, we could probably get on the order of half a dozen terawatts. There is hydroelectric, which is already used quite heavily, and it seems that it cannot add more than a very few terawatts. There's geothermal energy. One can argue about how much of it is actually recoverable, but again, over all land, that would give perhaps a dozen terawatts. There's tides and ocean currents that might give a couple. There's wind, important, but again, a total supply of perhaps 2 or 4 terawatts. You can compare that with the amount of solar energy that's available. 600 terawatts, practical. Of course, the total amount that hits the Earth from the sun is much bigger. It's 120,000 terawatts. But the practical one, 600, just looking at these numbers tells you that sooner or later, surely we have to start relying on solar energy. And that's what I want to talk about today. The cost of solar energy was prohibitive just a few decades ago. 30 years ago, 1980, the cost was on the order of 7 to 10 kilowatt per dollars, American dollars, per kilowatt hour. On this graph, the cost of the module is plotted, of the solar cell module. And on this horizontal axis, I show the total production, the cumulative production, how much solar energy has been installed. And so this is a logarithmic plot, and you can see something that will remind you of Moore's law in the semiconductor industry and in computers, the steady decrease of the cost. There are some bumps. For example, here there's a bump because for a while there was a shortage of amorphous silicon. But as you can see, the cost drops steadily, and it is related to the total accumulated installed power. So in 2010, you have 37 gigawatts, 2011, 68 gigawatts. This point here is 2012 that hit 100 gigawatts. That corresponds to this line here. And that corresponds to a cost that's about 100 times smaller than it was 30 years earlier. For 2015, this is the red point here, I've added that, the installed capacity is 242 gigawatts, or was. 2015 is in the past. And so if one extrapolates linearly, one gets the impression that this actually is going to be cheaper than burning coal and oil, and it does not produce CO2 and put it into the atmosphere. So this looks quite good, and it suggests that ultimately it will be the economics, not the politics, that will decide what will happen. When twice a year I start a semester, I have a classroom of students. I tell them, at the end of the semester, there'll be a final exam. You better start studying now so you know everything you need to know when the final exam comes. They listen to me, and they immediately dismiss anything that I've said. Say, no, this is infinitely far in the future. Why should I worry about it now? And I think this attitude that a disaster, a catastrophe, is not a disaster until it's at the door, is something that we have built into our DNA, that somehow, in some distant past, allowed us to survive. Of course, 3 days before the final exam, the students start coming to my office and they want to know what will be on the exam and should they study this and should they study that and so on. And this is a cyclic process. Every year it happens twice. And so it's the same with mankind. You know, you may start telling people that, yes, you know, in 50 years, half of Florida will be underwater. And they say, oh, well, you know, 50 years from now, I will not be here. Maybe my children will not be here. Who cares? So until the disaster is at the door, people tend not to take action. So it seems to me that the only way to avoid these disasters is to make electricity produced from sunshine, from sunlight, cheaper. Because then, of course, people will start using it. So this, I think, is a very good graph, encouraging graph, because this may take care of itself in a way. Of course, it would be good if we could improve the efficiency with which we convert sunlight into electricity. This is about silicon cells. Those are the kind that we normally use. And the efficiency is limited by something known as the Shockley-Queisser law, which says that if you just have a single junction, P silicon and N silicon, say, you can only get more than about 1/3 efficiency. That has to do with the fact that the sun is not a laser. It does not emit at one wavelength. It emits at all sorts of wavelengths. That's the black body curve, black body radiation curve. And so you cannot really choose the absorption edge of your material to satisfy all of those wavelengths at the same time. It will be optimal for one wavelength. Any light that has longer wavelengths, photons of less energy, will not be absorbed, so it will be wasted. Your efficiency will no longer be anywhere near 100% if you don't absorb the light. And any light that has photons of higher energy than that will waste that portion of that excess that is the excess. The excess will be simply converted into heat. And if you combine all of this together, you find out that about 1/3 is the best you can do. Now, the curve that's shown in blue illustrates what I just said. What I plot horizontally here is the so-called band gap. That's the amount of energy that the photon has to have to actually be absorbed. If it has less energy, in other words, if the wavelength is longer, then it's not absorbed. And you can choose that by picking one or another material. Silicon, for example, has a band gap somewhere here. That's near the optimum. And as you can see, the optimum corresponds to about 1/3. Other materials may have different values, and they might give you a little less than 1/3. Now, that's the theoretical maximum. You never actually reach that in practice. Although we do pretty well, you can buy cells that have on the order of 25%. That's not that much less than 32 or 33. And the idea that I want to talk about is, could we somehow get around that law? We cannot change what the sun does, but maybe we can be smarter in how we collect the sunlight and convert it into electricity and get above 1/3. Now, many of you may know that there are solar cells that have almost 50% efficiency. Those that are used on satellites, for example, or other objects that we send into the solar system. But those are not cheap cells. They do not have just one boundary between two materials. They have a whole series of these, and to produce them is enormously expensive. So if you want to pay $100,000 for a square meter, you can get an efficiency that's close to 1/2. But that's not going to solve the kind of problem that I'm talking about here. You cannot have that on everybody's roof. Whereas the cheap ones, you could have on everybody's roof. So, singlet fission. Why am I talking about singlet fission, and what is it? Well, let me first tell you that singlet fission would give us the curve shown in red. And that is not quite up to 1/2, a little bit less, but it's significantly higher than the blue curve. And so if we could improve the performance of solar cells using singlet fission, it would be a big step forward. So what is singlet fission? It's a photophysical process in which one photon is absorbed, and it produces ultimately not one, but two excited states. And each excited state can be used to produce an electron-hole pair. The electron is sent to one electrode, the hole to the other electrode, and you have a source of current and power. One can ask, how can you get something for nothing? Because obviously, if you get twice as many excited states, they will only have half the energy because of the law of conservation of energy. And it might appear at first sight that there's no gain in this. But it turns out that there is, because of the non-monochromatic nature, the polychromatic nature of the sunlight. You can start harvesting photons at higher energy without the kind of heat loss that brings you down to the blue curve from the red curve. I will not go through that in detail. So the way that the process proceeds is some chromophore, which is originally in the ground state, absorbs a photon. That's the process number one. That's just ordinary absorption. It produces a singlet excited state of that chromophore, of that molecule. Now, the first order description of that situation is that you take the energy from the photon and use it to promote an electron from the highest occupied molecular orbital, the one that's the highest in energy, and move it into the lowest available empty molecular orbital. And you can do that in two ways. You can keep the electrons' spins paired, and then you get a singlet state. Or you can flip one of them, then you would get a triplet state. The triplet state generally has a lower energy than the singlet state. They look the same. One electron is left in the HOMO, the other one is now in the LUMO, but the spins make a difference in the energy. And so what you now can do, if you have the right material, is to transfer this much energy, the difference between S1 and T1, from the molecule that did the original absorbing to its neighbor, which is in the ground state. And then this one ends up in its triplet state, and the neighbor also ends up in its triplet state. So this is a way to make triplet states out of singlet states without flipping any electrons. Why? Well, because these two triplet states are, at the moment they are born, still coupled into an overall singlet. So this is a spin-allowed process. And as a result, you now have two excited states, and these two triplets can diffuse apart and go to some boundary where they get converted into an electron-hole pair, and you start having a functional solar cell. In order for the process to be fast, this has to be a more or less isoergic process, or maybe slightly exoergic, that's even better. Because you have to have enough energy to bring this molecule up into its triplet when that one goes from S1 to T1. This is not a usual situation. In most molecules, organic molecules, chromophores, this gap is quite a bit smaller than that gap. And so singlet fission is very endothermic, and it takes place slowly. And that, of course, is a disaster, because that singlet fission has to compete with all other processes that the S1 can perform. For example, emitting a photon. And excited states will generally emit a photon within a few nanoseconds if they don't do something else. And so that means that this process, this singlet fission, in order to be really efficient, has to occur, say, 100 or 1,000 times faster. So it should occur in a few picoseconds. And the number of materials that are known that actually behave this way is limited. The process itself was discovered back in the 60s, and it was elucidated in general terms, and then more or less forgotten, until Art Nozick in 2006 pointed out that this might actually be good for solar cells, and he published this curve. The reference to his paper is at the bottom. So why don't we have singlet fission solar cells on the shelves in supermarkets? Well, because we don't have the right material. We have materials, about half a dozen of them, maybe a dozen by now, that behave properly. They do singlet fission fast enough to give a 200% yield of triplets, 2 triplets out of every photon, but they are not practical. They will not survive on the roof for even a few hours, let alone a few years. And so this has become a problem in material science, basically. If we had not 6, but 600 materials that give high quantum yield of triplets, a clever engineer would surely find one that meets all the other requirements that sensitizers have to have in the solar cell, and they would be on the shelves in supermarkets. There are many, many other requirements than just having 200% triplet yield. The material has to be sturdy and stable in strong sunlight. But it also has to have, about 24 other properties, matching properly the levels with the material into which the whole electron separation will take place, and so on and so forth. I think that we don't need to go into those details. But the need for new materials that would be good and efficient in singlet fission is obvious. So that's what this slide states. We need to find new materials. The ones that we have now are being studied. There are hundreds of, in the last 6 years or so, I think there were 500 papers on the subject. So this is a heavily researched area. But most of those papers focus on just two materials, pentacene and tetracene, if you know, and their derivatives. If you know anything about organic chemistry, you know you don't want to work with pentacene because you look at it wrong and it gets oxidized. And you don't want to work with tetracene. And so all these studies are useful in allowing us to figure out how the process of singlet fission actually occurs in detail. But they are not really producing, solving the problem directly. They are not producing new materials. So what is needed is some sort of rules that would tell the synthetic chemist what to synthesize, what to prepare in order to make a material that will be good and will ultimately satisfy all the requirements that are imposed. And this has two steps. The first step is to choose the chromophore itself. You will remember that the chromophore itself has to have the right positions of its energy levels in order for singlet fission to be isoergic or slightly exoergic. That's even better. Choosing the chromophore is problem number one. The other problem is, how do you pack the chromophores in the solid? If you have an isolated chromophore, it will never do singlet fission because you need two of them so you can have both of them in the triplet state. And then the question becomes, well, if you just look at a dimer, should the dimer be this way or that way? What is the best arrangement? And the choice of chromophore packing is what I want to talk about today. We work on both of these aspects, both theoretically and experimentally, but in 1 hour it would not be reasonable to try to tell you about everything we do. So I have chosen to talk about how to choose the chromophore packing. So what does this call for? What we want to do is to optimize the mutual positions of two rigid bodies. That's a simplification, right? Because in any real material, you will have many molecules knowing about each other, not just two. But you have to start somewhere. So let's start with two. The mutual orientation and disposition of two rigid bodies is a function of, or can be described by 6 variables, because you have 3 degrees of translation that are independent, and 3 of rotation that are independent. So if you have 6 variables, you need to define some sort of a search function which would tell you how likely is singlet fission versus all other competing processes. And you want the local maxima of that search function, but you want it in 6 dimensions. So if you just have 10 points in each dimension, a grid, that's 1 million dimer geometries at which you have to evaluate the search function. Now, in principle, you should also evaluate the competing rates. That sounds difficult. I mean, that sounds like a lot of work. The alternative would be to come up with some sort of a qualitative rule that does not require you to actually perform those calculations by gazing intensely enough at the expressions that tell you what the rate of the various processes will be. Well, so how do we proceed about this? And I think this is sort of an example of how computational or theoretical material science can be done these days. It happens to be chemistry here, but one could imagine situations that would be similar in other disciplines. We write, first of all, the general expression for the rate of a process known as the Fermi golden rule. And it tells us that the rate will depend on the square of a particular electronic matrix element and on a term that describes the density of states in the product you're making. That I'm not going to talk about directly. It can be handled by Marcus theory. That's the theory for charge transfer, for which Marcus got the Nobel Prize. And ultimately, it reduces into what happens to the reaction energy. That's because when you have two molecules, even if separately, they have the right positions for the S0, T1, and S1 states, after they interact, those positions will change. And if the S1 drops relative to the T1, then no longer do you have the isoergicity that you had in principle. And so you have to look at that, and that comes from this. And there's another thing, the so-called reorganization energy, which tells you which relates to the fact that the geometries of the molecules before and after the event, before and after the singlet fission, are not the same. And if they are very different, this term becomes large. What I'd like to do is to focus on this electronic matrix element and then ask the question, could I find the local maxima in that six-dimensional space? There may be many of them. I'm interested in those that have the largest values of this matrix element square. Now, one can do things in more detail. I will not explain it here. What we'll do is actually find those maxima, the local maxima in the 6 dimensions, and then ask for the best dozen or 2 dozen or 3 dozen, how they satisfy these other conditions. And those that don't, we'll just delete. Okay, so suppose you say, fine, what is that matrix element square, this TRP, equal to? Well, you can use a simplified theory, which leads to the expression given here in the first 2 lines. It is a sum of 2 terms. Both of them are integrals. One is called direct, the other one is called mediated. That's a little more complicated. It's a product of some integrals. And this is already simplified by neglect of second and higher powers of intermolecular overlap. That is the overlap between orbitals on one molecule with orbitals on the other molecule. Now, the expressions do not look very friendly. This direct term is equal to this. These various things are integrals. This is an integral that represents the electrostatic interaction of an electron, of a charge density that is produced by multiplying the lowest orbital on partner A, that's unoccupied, the LUMO, and the highest on partner B, that is occupied. And here, similarly. And the evaluation of these integrals can be done, but it's not all that fast. And this is the direct term. The indirect term, or the mediated term, looks worse. So, looking at these equations, how do we come up with a simple rule? You know, a one-sentence statement telling the organic chemist, this is what you need to synthesize. That's the subject, actually, of the work that we're doing. So how does one proceed? Here I just illustrate for the simplest example of a pi-electron system, ethylene, what one is up against. You could initially superimpose the 2 ethylenes, and then you could do a translation along X, Y, and Z for one of them, move it here, and then do rotations around X, Y, and Z to get it into the orientation in which it is. This just simply demonstrates the 6-dimensional nature of the problem. And if you want to search through all of that space, you probably don't want just 10 points along each direction. Here we use 0.2 angstrom for the translations. That calls for 47 steps. And we use 10 degrees for the rotations. That's 19 steps. And so you need calculations at 712 100 million of dimer geometries. Now that looks hopeless. It's almost 1 billion. But when you remember that a week has about as many milliseconds, also close to a billion, then you just need to draw the conclusion that all it takes is to calculate 10 or 20 of these geometries in a millisecond. Well, you won't do that with the formulas I have shown you. No computer today can do that with that formula. And so the logical conclusion is, let's make some approximations. Let's make physically justified approximations. They don't have to hold everywhere. They just need to hold in those places that are close to the local maxima. Those are the only ones we care about. So, for those people in the audience who know about theoretical chemistry, the list of approximations that we have made to this formula is given here. It will make sense. To the rest of you, it will make no sense. It's just words. But after you make those approximations, those pages that I showed you simplify into a single line. This is the line. This is the expression for the square of the matrix element. And this is so simple that you can actually calculate 10 or 20 of them in a millisecond in today's computer. And so we were able to actually do this search through the six-dimensional space and do those 700 million calculations. Now, it just took a few hours. For a bigger molecule, ethylene is not a practical molecule for solar cells, but for a bigger molecule, it takes a little longer, maybe a day or two, but it's feasible. So what does this formula say? And could this formula be something that can be converted into a single sentence for the synthetic chemist? Well, what does it say? This is a proportionality constant that can be evaluated once and for all. It's related to the electronegativity of carbon, because we're dealing with mostly with carbon-based molecules. And here we have a product of four sums. This sum, that sum, this sum, and that sum. They are divided by some energy differences. Those energy differences have to do with the amount of energy that's needed to transfer an electron from one of the partners to the other partner. And it does not depend very strongly on how the molecules are arranged, as long as they are in contact. So for simplicity, we could just say, let's pick 1 electron volt or 2 electron volts for these. That's not going to have any effect, really, on the location of the maxima. It will have an effect, it will scale the magnitudes, but we don't really care about those. We want to know what the geometries are. What are these other numbers that are in here? Well, the C's are the expansion coefficients of the lowest unoccupied orbital, the CL, and of the highest occupied orbital, the CH, and they are combined in different ways. One of them is on partner A, the other is on partner B, in all of these. Now, these are numbers that tell us how the molecular orbitals are distributed over the molecule. Where in the molecule they are big, and where they are small, or where they have zero amplitude. But that's something you just do once, and you know what they are. So that does not hurt. That's easy. The only thing that changes with the geometry are these symbols that I called S. Those are the overlaps of atomic orbitals on one partner with an atomic orbital on the other partner. Well, most of the time, if you just draw the two molecules, you can tell which overlaps will be big, which ones will be small. But you can actually calculate them in a very, very fast calculation. Those are the easiest molecular integrals. And so this is a simple result published with Zdeněk Havlas. He wrote the program to actually do the evaluation at those 712 million geometries. Well, you can actually do better than just a calculation. You can say, could I deduce a simple rule from this equation? Let me illustrate that on the case that's simplest, that's the two ethylenes. If you actually substitute the molecular orbitals, the highest occupied and the lowest empty, for ethylene into that expression, you get this. Now it's really simple. It says that the rate will depend on the square of this difference. This is one overlap multiplied by another overlap. This is one overlap multiplied by another overlap. What are these overlaps? Well, suppose you take the two ethylenes and you stack them on top of each other like this. Then this is what they would look like. And so one of these products would be this overlap, which is good, it's pretty good, multiplied by that overlap, which is smaller but still non-zero. And from that you subtract this overlap multiplied by that overlap. Well, from symmetry, you see you get zero. And so indeed, this is a bad geometry. In order to make something bigger, get something bigger than zero, what you want is to have one of these products large and the other one small. So, what does that mean? That means that you want one orbital on the top ethylene to overlap with both at the bottom ethylene, and you want the other orbital on the top ethylene to overlap with nothing, or maybe at most with one. Here you see this overlap is small now, and so that product, this and that, will be small, and you collect some nice value. It doesn't have to be just this. You could arrange the molecules this way. Now this orbital on the top ethylene overlaps with both at the bottom ethylene. The other one doesn't overlap with anything. Similarly here. And so you can actually state a simple rule in a sentence like that for ethylene. Now, ethylene is not interesting, but it's a model case, the simplest case. Can this be generalized? It can. You can actually do a little algebra and discover that the rule is general in the following sense. If this is what the lowest unoccupied orbital looks like in your chromophore, I've chosen anthracene as an example, and this is what the highest occupied molecular orbital looks like, the colors indicate sign. So this orbital would have one sign here, the opposite sign there, and similarly all around. So would this. So what you do is you first define the sum and the difference. This is the difference of those two orbitals. This is the sum of the two orbitals. You see, they are semi-localized. This one is mostly localized at the bottom edge. This one is mostly localized on the top edge. And now you use the same rule that we deduced for ethylene here, and you get the result that looks pretty much the same. What you want is for one of the ethylenes, say the top one that I show here in full lines, to be such that it has an overlap with one of the localized or semi-localized orbitals of the bottom ethylene. That would be this one. You have an overlap here, you have an overlap there. I have taken the two anthracenes and shifted them this way, so they are not quite on top of each other. I know that if I had them on top of each other, I'd get zero. So here, this orbital now, the one that's localized on the top edge, overlaps with both the minus and the plus combination of the top anthracene. And the other one does not overlap with the orbital that's localized here at all. It still overlaps there. If you look at it from the side, you get a picture something like this. This orbital can interact here and here. That orbital overlaps a little bit there, but doesn't overlap at all there. And so this is supposed to be a good geometry, according to the simple rule. And actually, this is the geometry in which pentacene and tetracene actually crystallize. And this is one of the reasons why they are so good in doing singlet fission. We can understand it in very simple terms. The fact that this is tilted away is also important. You could have this parallel. The two planes of the two anthracenes could be parallel, and you would still have the same thing. You would have overlaps here and here, but you would not have an overlap from here to there. This is better, not because of the TRP matrix element. It is better because of those other factors that I said I will not talk about, the effects on the energy. You have much less Davidoff splitting here than you would have if they were parallel to each other. So we now have simple qualitative rules that tell us how to put the molecules together. And moreover, we have a computer program that can, in a few hours or a few days, depending on the size of the molecule, evaluate these matrix elements square. And so here are the results, the top 6 for 2 ethylenes. And you can see that this is the best. And this is, of course, just what we saw, 2 ethylenes shifted this way. This one is almost as good. These numbers are the squares. And this one has the 2 ethylenes this way. What I show is the ethylenes with their atomic orbitals and the projections into the 3 sides of the bounding octant. These are the numbers that result from the other considerations that I didn't talk about in detail. They tell me that this is not good, although it has the best value of the square, because of the Davidoff splitting. This one is much better, has 0 Davidoff splitting. So if I were to make a solar cell from ethylene, which would be foolish, this is the geometry I would try for. Interestingly enough, all of these elements increase if you get the molecules closer together. So the best place for these solar plants is the very bottom of the ocean. The trouble is that there's no light there, but singlet fission would go very well there. So you can do this for ethylene. We've done it for bigger molecules also. I show results for one dye that's related to indigo, where again, the best geometries are shown here and here. But this geometry is really the one of choice because it satisfies those other criteria that I didn't go into any detail about and that correspond to the numbers listed here. And this can be done, as being done now, right, actually, for all kinds of other molecules as well. Now, I should admit that knowing what to have is not the same as having it. The synthesis, the crystal engineering or synthesis of covalent dimers is still ahead of us. That needs to be done. And that's a huge amount of work. But at least we know where we're going. We know what to shoot for. Now you could ask, how do you know that those approximations that you made are any good? Let me provide some evidence for that. If I just look at a 2-dimensional subspace of my 6-dimensional total space for 2 ethylenes, and I say my 2 ethylenes are in parallel planes, and they are stacked, and I shift them in this direction or that direction, x or y, and the z is fixed at 3.6. That will be 2-dimensional, and I can plot the value of the square of my matrix element, and I get this if I do the exact evaluation. That was a fairly big calculation, but it was done. And I get this using the simple approximate one-line formula. And the absolute values are not the same, but the positions of the local maxima are nearly identical. You'd be hard-pressed to see the difference between these two. What you can also do is take the exact values, well, they are exact within the model, and compare them with the approximate one-liner, and you get something like this. So, and this is without any fudging factors. This is how it comes out. So, yes, for the large values, you get a pretty nice agreement between the two. The line shown is the line for perfect agreement. For the small values, there's basically no agreement, but we don't care about those. We really only care about the large values. And so we think that the simple method actually will have merit and that the results will be meaningful. Okay, to summarize, I've only told you about a fraction of what we are doing, and that's only a small fraction of what a whole lot of other people are doing. But it's meant to give you an idea of how one can proceed with solving a problem like this. So this model that we're using is approximate, but we have been able to formulate a qualitative rule for optimizing this square of the matrix element. And it's simple enough, the formula is simple enough that we can actually do searches in 6-dimensional spaces that require close to 1 billion evaluations, close to 1 billion geometries. And we can do that not only for the matrix element I talked about, but also for these other properties that I skipped. And then we can use these other properties to eliminate those of the local maxima that are unsuitable for other reasons than just the value of the matrix element squared. Well, I think that I have just about run out of time, and would like to now thank my collaborator, Zdeněk Havlas in Prague, and Eric Buchanan, my graduate student in Boulder. And I would like to thank you once again for the invitation, and thank you very much for your kind attention.
Okay, thanks, Professor Michl, for the beautiful presentation. And now it is open for questions, curiosity. Come on, don't hesitate.
So in the singlet fission process, do you need a coupling between the triplet and the singlet in the single monomer for that to be allowed, or is it just the overall process?
It's the overall process. Actually, you do not want the S1 and T1 to be coupled. They would be coupled by a small term in the Hamiltonian known as the spin-orbit coupling in organic molecules. And that would be bad because it would allow a process in which the S1 state goes into the T1 state plus heat. And you would only get one excited state.
I have another question for you. This is a more general one. So one of the criticisms you often read about solar energy is that they often write that the energy expenditure to produce, install, and dispose of the panels in terms of both energy and CO2 is greater than the savings that you get. You read this a lot.
No, that might have been true 30 years ago, but today the energy cost of the panel is recovered in about a year.
Okay.
And the panel is supposed to last about 30 years.
Thanks.
You need 10 years to plan it and build it before it produces 1 kilowatt of energy.
Yeah, yeah.
So, other questions or observations? Yeah, sure.
Joseph, you have presented the Fermi formula as if the singlet fission process would be a rate process. But actually we are looking for a very fast process, so it's more like a dynamical process.
That depends on the system.
Yeah.
In a few molecules, particularly pentacene and its derivatives, the singlet fission occurs within 100 femtoseconds. And there you want to consider factors such as coherent excitation of the biexciton, the triplet state, and the initial S1 state, and things like that. But in most molecules, it's a slower process. Tens of picoseconds, maybe even hundreds of picoseconds. And then the electronic coherence is lost, and you can use ordinary kinetics.
And nevertheless, the electronic part of what you said, because you simply skip the density of states and all that. But the electronic part of what you said, the coupling, is more or less the same. We can anyway rely on your theory to know which dimers are well coupled, even if the process will be very fast.
Yes, that is true. The matrix element is the same regardless of what the other events are. And also I should add that if the singlet fission is sufficiently exoergic, and in pentacene it is, in hexacene it certainly is, well, that's totally impractical, well then it may not be so important how you pack the molecules, because even if you pack them poorly, it's still sufficiently exoergic that the process may outcompete all other processes and you're still okay. But in most chromophores, that is not the case. In tetrazine already, it is not the case. And in that indigo derivative that I showed here, it is not the case. In that indigo derivative, by the way, you have the right positions in the isolated molecule of the S0, T1, and S1. But when you put them together into a crystal, they have a fairly large excitonic interaction, and the S1 drops. And instead of getting 200% triplet, you get something like 40% triplet, which is, of course, totally useless. You know, anything less than 100% is totally useless. Actually, you have to be pretty close to 200% to make it worthwhile. You know? So in that case, and in many other cases, what you see is excimer emission, exciton emission. And that's just a trap into which the system falls, and then it never does singlet fission. In a sense, you know, every system, it needs to be looked at as a separate entity, and they all differ from each other in some ways. This is what I'm talking about is like saying, you know, all people are equal. I'll use the same shoe size for all of them. In reality, once you start studying a particular system, you have to look at it more closely.
Well, I have another question. You just touched the point. To put the two chromophores in the right relative position, you either rely on crystal engineering. I guess that means putting substituents and things that keep that favor the right packing in the crystal, or dimers. So
you can synthesize covalent
on organic
dimers.
chemistry
Yes?
to make a molecule of the right shape. Which one is more practical for the final needs?
I do not know the answer.
We need a crystal, or do we prefer molecules?
I do not know the answer to that, and we're trying to do both. For example, in this molecule here, this is what we see in the crystal. They are parallel above each other, just slipped. And that's bad for the reason I stated. This is what we would want. So we want one of them to turn like this. If you turn them 90 degrees, then the Davidoff splitting is 0, you get the best situation. But already 60 degrees is very good, as you see here. So we have a substituent in this position here, a phenyl, and in that position there. And when they stack like this, it's bad. So what we're doing is putting 5 fluorine atoms on each phenyl substituent, because it is known that perfluorinated benzene rings like to stack with ordinary benzene rings, not fluorinated. And so the hope is that if we have that on here and here on both molecules, well then the molecule will prefer to do something like this, where the fluorinated benzene rings would be above the non-fluorinated benzene rings of the other molecule. That's crystal engineering. Whether it will work or not, I have no idea, but we'll try. So we are at a rather primitive stage in crystal engineering. It is possible in some cases to predict what will happen if you change a substituent or something like that. In many cases, nature surprises you and it crystallizes in some completely different form. So it is tricky. But the synthesis of the covalent dimers is not without pitfalls either. You have to connect the dimers in a way that does not conjugate one to the other. And you have to do it pretty accurately. What I show here is the value of the square of the matrix element or the matrix element itself for 2 tetracenes. Again, in the same 2-dimensional subspace. You can move them this way or this way. And you can see how moving the atoms sort of sitting above each other or between each other makes the function jump up and down like crazy. The diameter of these anthills. I suppose they would be termite hills, right? It's about 1.3 angstrom at half height. And that means that you can afford to have a little mistake in the positioning, but you cannot afford to be off by 2 angstrom. So the synthesis of the covalent dimer has to produce the desired structure fairly accurately. And so that's tricky too.
Hi. I was wondering what kind of algorithm you used for performing the search.
Well, we constructed the grid, so we had all these points, and then we looked at for local maxima in the function by comparing the magnitude at each point.
Yeah, I mean, so you
with
just
its neighbors.
search through the whole grid?
Yes, the whole
right.
6-dimensional space.
Okay.
Well, that's not a good statement. Of course, it's not the whole 6-dimensional space. Only that part of the space in which the 2 molecules are in contact. Okay. This is why we were able to get away with only 47 grid points in the translational directions. The whole space, of course, they could be far apart, but then you know that the matrix element will be 0. You don't need to calculate that.
Okay. All right.
Other questions? So, if there are no more questions, we thank again Professor Michl for its contribution. Thank you.
Thank you.
So we ended the first round of small research on singlet fission. We did dynamics. And well, in the first round we were completely knocked out in the sense that
You were completely
the
what?
compound we tried prefers to decay to the ground state, and it does it very fast.